This is a video on string theory. So this is sort of like an extension to the standard model of particle physics for year 12 for HSC physics. In the last module, from the universe to the atom. So string theory is a possible answer in terms of unifying all the known forces, all the known particles and gravity into one framework, into one grand unified theory. So it's a possible GUT for short, as physicists call it. GUT stands for Grand Unified Theory. Okay, so the standard model of matter, standard model of particle physics, has the limitation that it doesn't include gravity. Doesn't include gravity. Okay, includes all the other forces of nature, electromagnetism, the strong and weak nuclear forces, but it doesn't include gravity. Okay, so string theory manages to do that, manages to include gravity into this holistic framework. So what is string theory? Well, it postulates that all the fundamental particles in the universe are made of oscillating strings of energy. Okay, so picture, let's say, an electron, okay, which is believed to be like a point-like particle. Okay, this diagram is a bit misleading because particles don't have a size. Okay, they're points, they're zero-dimensional entities. So an electron, according to string theory, it's a mathematical theory in theoretical physics, postulates that electrons look like this. Okay, so very far away, a string appears to look like this on the left, as though it's a point, a particle. Up close, an electron looks like this, a vibrating string, like a rubber band, if you wish. Okay, string of energy. Okay, oscillating at a particular frequency, okay, a particular rate. Also, let's say you've got a quark, let's say a top quark. That's also pictured to be like a string of energy. It's a very elegant theory. And it's believed to be a unified theory it's believed to be a unified theory because everything can be expressed in terms of one, just a simple object, a string of energy. And if I, let's say, pluck this string at different rates, I'll get all the different particles that exist. So electron, let's say all the quarks, so the leptons, let's say the quarks, the bosons, in the standard model, all the particles, you get all the particles, okay, from a simple entity, a string of energy. And the faster the string vibrates, according to string theory, the heavier the particle. So let's say, in this case, we've got a string like this at the top. At the bottom, we've got a string like this, not vibrating much. Okay, that's lighter. Let's suppose the heavier particle is a top quark. Lighter particle is an electron. Okay, the faster it vibrates, the heavier it is. Okay, because the more energy it has. Okay, you can think of it as E equals mc squared. Okay, you've got more energy in the string, therefore we have more mass. Right, heavier the particle. How long is the length of string? People would ask. Well, it's believed that a length of string, if you were to cut this, take a string, cut it open, lay it out, 10 to the minus 35 meters. Okay, that's 0 point followed by 35 zeros. Okay, and anything that's shorter than this doesn't really make any physical sense. Okay, this is called a Planck length. Okay, this is the shortest possible length you can ever have. Okay, named in honor of Max Planck, the father of quantum physics. And what's even, so what also comes out of the maths of string theory is that you can have both open and closed strings. Okay. And strings, it's worth noting, these are one-dimensional entities, okay? A straight line is one dimension. A point is 0 dimensions. A square, let's say, is 2 dimensions, okay? Dimensions, so 1 dimension in this case, you've got left going left and right. 2 dimensions, up and down, left and right. Okay, 3 dimensions, up and down, left and right, back and forth. You get the picture. Okay, so they're one-dimensional entities. And here's where it gets a bit weird. You need 10 dimensions of space, okay? Most modern current string theories postulate that you need 10 dimensions of space in order for these strings to exist, okay? The question then becomes, so we live in a three-dimensional world, okay? 3 dimensions of space, left, right, back, forth, up and down. Okay, so cubes are 3-dimensional. Where are the rest? Where are the 7 other dimensions? It's believed that they're actually curled up, so small that you can't see them, okay? So if you had a super powerful microscope, you might be able to see them. Okay, they're curled up like so. Okay, with different geometries. I can't really draw it here because it's very complicated. But they're called, they take the shape of what are called Calabi-Yau, I don't know if that's how you pronounce it, manifolds. Okay, these are the shapes, the forms of the extra dimensions that we can't see, if this theory is correct, if string theory is correct. Okay, so string theory not only unifies all the known forces of the universe and the particles, but it also postulates that there's extra dimensions that we can't see. And one other thing, open strings. So I talked about open strings. It's an open string. This is a closed string. The fermions are believed to be open strings, whereas the bosons are believed to be closed strings, according to the mathematics. So, for example, the quark, the electron, okay, might look like that on the left, open strings. Bosons, the photon, the gluon are believed to be closed strings. And yeah, there's been no direct experimental evidence for string theory to date. Why is that the case? Well, it could be because the energies to reach, well, it's not because, not maybe, it's because the energies required to tap into these extra dimensions is extremely high. And to make these, and to be able to see these strings, it'll require a lot of energy. So that's string theory in a nutshell, and that's a great extension for the HSC particle physics segment. Okay, so it's a great thing to put in your long response questions if asked in the HSC on the limitations of the standard model of matter. Okay, and just one extra thing before I move on, before I finish this video, the Calabi-Yau manifolds. Here's a crazy number. There's 10 to the 500 possible ways of compacting, of curling up these extra dimensions. 10 to the 500. And what's worse is, so this number is known as the landscape because of all the possibilities. Which one of these landscapes corresponds to our universe? That's also an outstanding question that string theorists haven't answered yet. There's 10 to the 500 possibilities. Which one corresponds to our universe? That's still unknown. But that's string theory in a nutshell.